Let's have a little fun with some actual data, applying some of our filters and smooths so we can begin to get a little bit of an idea of how they behave and what the output looks like. I'm running R. I'm going to begin here by loading the programs that I made available for download. I generated some random noise earlier, and I'm going to load that up, and I'll make a nice little plot of it, as well as a plot of what the signal is behind it. There is no signal. This signal itself is just zero, because the data here consists entirely of random noise, and it's white noise. We want to do some smoothing and see how well it does at finding the true signal. In this case, that's going to be an easy comparison because we know what the true signal is. This is artificial data, which doesn't reflect real physics, but there's a huge advantage to artificial data, namely, you know what the answer is, so you can compare your results to what the true answer is. Artificial data is a great way to explore methods, how they behave, and how reliable they may or may not be. Let's start by computing a time average over each year. T is the times, X is the data values, and I've told it 1 to average over each single year. Now the times going in are monthly values, so there are 12 of them each year. So I'm really computing average where I divide time into slices 1 year wide each, and I average all 12 values within each one. The program makes a nice little plot for me. It also returns a bunch of values, which I've stuck into a variable called Q. That's kind of my default junk variable. But Q isn't just a numerical variable, it's a data frame, so it contains a lot of different pieces of information. If I look at the names of what's in that particular data frame, I can see what it returns for me. It returns the average time within each time slice. So it takes each year's worth of data and averages what the times are within that year. It also computes and returns the average data value within each year. It also reports to me how many data points were in each time slice. The TIMAV program doesn't have to have evenly spaced data. It could have irregularly or unevenly sampled data, in which case each year might have a different number of data points in it. It will report that for you. It also reports the standard deviation of the data going in to each time slice. It also reports the standard error of the average coming out of each time slice. Finally, it reports these low limb and up limb values, which are lower and upper limits for a 95% confidence range. Now, these are kind of fancy values in this particular program. What we're going to do generally is we're just going to take the average value we estimate, the smooth value, and we're going to add and subtract 2 standard errors to get our 95% confidence range. Well, that's fine, but it kind of assumes that the average itself is following the normal distribution. Well, in most cases, that's an excellent approximation. But if you have a very small number of data points going into the average, only 2 or 3 especially can be very small, you really shouldn't use the normal distribution. You should use the t-distribution. So this particular program uses the t-distribution to compute its confidence limits to give you a 95% confidence range. Another thing is, in the filters we apply, we need to, in order to compute the standard error of the smoothed value, we need the standard deviation of the noise. We're going to estimate that by the standard deviation for the whole sample, not just what's in the window we're averaging. Well, for this particular program, it computes each standard error based on the standard deviation estimated within only that window we're averaging. So that's another difference in how we're going to compute standard errors in the other filters. So this has a very fancy way of doing its confidence range. Let me plot it in a slightly more friendly way. Here we can see the average values from each year, from each time slice. We can see that they wiggle around, they show noise. That after all, the data had noise going in. In fact, the data were nothing but noise. So what comes out is going to have noise in it too. But hopefully it will be noise that will not be too far from the signal. The signal is shown by the thicker red line at 0 because the signal is 0. There's really no signal here. And we can see that it does pretty much what we expected. It wiggles around, not as much as the original data. We have reduced the noise, but it's wiggling around the true signal value, which is 0. I can also compute that error range. Well, it's already computed. I can plot it. So we would expect that the true signal value is within that confidence range most of the time, and it is most of the time, not all of the time. If we look here, we see that the confidence interval does not include the true value, which is 0. Well, that's just a fact of life. The confidence interval is based on statistics. The numbers that come out are random. They have randomness in them at least. And a 95% confidence interval will not include the right answer about 5% of the time. So it's no surprise that some of our confidence intervals do not include the true signal value. Well, we can compute an average over longer time spans. We could compute averages over every 5-year time span. This would divide time into 5-year slices, compute for each one an average, and a 95% confidence interval for each one. We can see that even here, we've got a couple of intervals where the confidence interval does not include 0, which is the true signal value. Here's one. Here's another one at the very end of the time span. We can make a slightly friendlier plot, perhaps, like this. And we can add on, this time instead of plotting a dashed line above and below, I've plotted error bars. It's really the same thing. You can see that if I plotted dashed lines, it's really the same confidence interval throughout. Well, we could even try 10-year averages. Divide time into 10-year slices and average within each one. And once again, we get averages and confidence intervals for each 10-year wide interval. Once again, we see there are some cases here and here where the confidence interval does not include the true signal value. That's the way that randomness is. Sometimes, about 95% of the time, a 95% confidence interval will include the right answer, but there's going to be times when it doesn't. In this case, there are actually 3 of them here, well, 4 if you count this one. So this is one where just by accident, there were quite a few intervals that the confidence range did not include the true value. By the way, when we split time into 10-year slices, an average within each one, we started at 0, then we put a boundary at 10, then we sliced at 20, 30, 40, etc. You don't have to have those be your time slice points. You can offset where you're going to start each interval. There's an option in the TimAv program called t.off, where you can specify how much you want to offset where the averages start. Let me run this with a time offset of 5. It's really kind of very similar because, once again, I am computing averages over time slices that are 10 years wide. But this time, the first and last slices have larger standard errors. That's because they have fewer data points. They only had 5 years in the first slice because at time 5 years, I sliced it into pieces. I can even make a plot, since the TimAv function reports how many data points go in each one. I can even make a plot showing how many data points went into the slice at each time. Notice that most of them are 10-year averages of monthly data, which is 120 data points per decade. But the first one and the last one only had 5 years of monthly data, which is only 60 data points for monthly values of a 10-year average.